Yeah, so for today's class, we'll be doing work, energy, and power. Check that notification out. So we're doing work, energy, and power. So it's physical science. Work, energy, and power. Yes, so work in everyday conversation is used to mean different things. We talk about going to work, doing homework, working in class, working out. Physicists mean something very specific when they talk about work. In physics, work is used to describe the process of transferring energy from an object or system to another, or converting energy from one form to another. Okay. So transferring energy from one object to the other. So there's a billiard ball traveling at a certain speed, and it's gonna hit another ball that's sitting there, and once they have hit each other, then you get this one stationary and this one moving away. So you get something like that. That's the transferring energy from one body to another. Transfer from one body to another. And in the other case, to change from one form to another. Remember crumple zones from momentum? Yeah. The kinetic energies deforms the car and then changes to something else. And then key concepts, units and unit equations, techniques of vector addition, Newton's laws, and force diagrams. The definition of work is the force times change in displacement times cos of theta. And this would be when a force acts in or against the direction of motion of an object, work is done on the object. So it could be there's an object that's already moving, and it's moving towards the right, but then there's a friction doing work also on it. So there'd be friction, and there'd be the force moving it forward. What? The video. Okay. So there's a force moving the block. And then moving a block. Yes, you are. This means that in order for work to be done, the object must have its position changed by an amount delta x. So by this amount, that's the distance x must traverse. So x, that's the distance block A rather must traverse, right? You can't see. Oh, traverse. Okay, good one. But this comes from the basic definition that work is a force applied over a certain amount of distance. Okay? And that becomes the change in x direction, the lateral motion. And I guess the cos x is to accommodate for a change in inclination. So I'll just put this in yellow. and say this accommodates change in inclination. Accommodates, so inclination just means angle from the horizontal.
Elevation.
Accommodates change in elevation. And this here is the lateral distance. Let's just make it blue. So this here would be lateral distance. Lateral distance. And then this here would be the force that is applied onto the object. So F. So this would be the force applied onto the distance, onto the block over that distance. This means that in order for work to be done, object must move by about a distance of delta x, while a force is acting on it such that there is some non-zero component of the force. So in other words, there has to be a non-zero component of the force. So the force can't be equal to zero, nor can it have, in the direction of the motion, a zero component force. Otherwise it's sitting still, it's not moving. Right, so work is work done in joules. In joules. F is a force applied in newtons. So force applied in newton.
Displacement.
Delta x is displacement.
In meters.
And the angle is the angle between the force and the direction of the displacement. So angle
It doesn't decrease.
in degrees, yes, that's correct. Between the force and direction of displacement. Like that. Okay. Yeah, and that's simply something that looks like this. So that would be theta, and let me use a yellow color for it because it's in yellow. And it was all yellow. And then delta x would be, so delta x would be in that direction, and the force would be in that direction. Alright, so just take it, fade it back to black. Okay, so cos theta tells us the relative direction of the force and the displacement, which is important. If the component of the force along the direction of the displacement is opposite in direction to the displacement, then the sign of the displacement vector and the force vector will be different. So this just explains that if there is a force acting on the object and the horizontal component is now acted upon by another force in the opposite direction, then the cos theta accommodates that. So that's why we had the negative 180 degrees in some of the problems that we were solving for over the weekend.
Again, cos 180 gives you negative 1.
Yes.
And then
So-
cos 0 gives you 1.
Yes. So the negative 1 you get, but it gives you a negative value for this part here, for the whole part really.
Yes.
And that's because if it's negative, then it's in the opposite direction because it's a vector, because the force is a vector. So if it's in the opposite direction, then that's where you have things like friction, because it normally acts in the opposite direction to the motion, to the primary direction of motion. Yeah. All right. So, yeah. So if we have 90 degrees, for example, and the force is acting vertically upward or even downward, then that doesn't count as work because there's no displacement to the left or to the front or to the back or to the left or to the right. So it's like picking up a box from the floor or pulling up a car with an electromagnet. There's no movement.
The only force applied is
vertically upwards and downwards.
And energy. And then maybe tension.
Maybe tension can be accounted for. But in terms of work, as we're looking at it now, that doesn't count. So if we have
above the x-axis.
Yes, it's above the x-axis. So if we have a force applied, and then we get a scenario where the box is just lifted up from the floor. It's supposed to be arrow and force. So there's no movement in the lateral direction. That means then delta x is 0. Then that means the work done, because theta is 90 degrees and cos of 90 degrees is 0 degrees. Oh yeah, happy. I won. And then if we have
cos 90 is 0.
Cos 90 is 0. Yeah. But if we have now as theta increases, let's say theta acts in that direction, then there will be a horizontal component and a vertical component, because the force is pulling both in this direction and that direction. Right, so then that means, and this is theta, then theta is greater than 90, then cos of theta will be negative. Then cos theta will be negative. Right? And that simply means then that our force acts in the negative direction. And I guess you could flip these this way. So with cos of 0, so we can start like this. So with cos of 0, okay, let's say cos theta, and theta equals 0 degrees, then we have something that looks like, oh yeah, cos theta equals 1 at theta equals 0. So then we'd have f cos of 0 which equals f. Right? And then cos of theta equals 0 at theta is 90 degrees, and then we have something that looks like this. And delta x is 0, but also, let me rather not say delta x is 0. Let me rather use the cos. So f cos of 90 equals f times 0, which is
either way, even if delta x is 0, it means the work done is 0.
Yes, that is true. So there's no, still means the work done is 0. Yeah, so it goes two ways. Yeah, goes more than one way. Cos of theta is let's say -1. At theta is 180 degrees. So then that would be something like that. Maybe friction. -F. And then we also have cos theta is less than 1. Than 0, sorry. At theta is between, let's rather use inequalities. So theta is between 1 and let's say theta is between 91 degrees and 270. Because cos of 270 is 0, right? Yeah. Yeah, so between 91 degrees and 270. And then also cos of theta is greater than 0 at theta from 0 degrees to 89. So it also fits with cast. Yeah, so
All students take coffee. All students take coffee.
All students take coffee. Cos all sine 10. That's what it is. But yeah. This investigation, you can self-study that. But let's just go through some of the theory. Worked example. Okay, a car is traveling along a straight line. So worked example number 1. And this is on page 224 of our Siyavula learning guide. Siyavula. Calculating work on a car when speeding up. All right. We've got a car that's traveling on the road, and on this road
It's traveling in the direction that it is speeding up.
the car is speeding up, and a force for it to speed up, a force of 500 Newton is applied.
And so a force is applied in the direction
that the car is traveling in.
So our theta is 0.
Alright, so then we can put that down, definitely. And while it is speeding, it covers a distance, delta x equals 20 meters. Or rather, whilst it is increasing its speed or speeding up. So speeding up, so the car speeds up, or the force is applied over 20 meters. So then, over the next 20 meters, so that the car is somewhere here. I'll just say the screen ends there. Alright. Now we must find the work done on the car. Find work. So we must find how hard the pedals of the car, or how hard the acceleration of the car has to, how much work the accelerator is putting on the car, the engine is putting, yes. work done on
How
a
much
car.
energy is required for this car to move faster? For this car to speed up?
How much energy might mean something else. Remember, we're still dealing with just work here. Yeah, so in terms of work, it's probably best to say
How much work is done for the car
to speed up over the 20 meters. To speed up over 20 meters. All right, cool. So we know that the force is applied and it's 500 Newton. The distance is 20 meters. Theta is 0 because the car is moving in the same direction as the force that is applied to it. And then we must now use that definition. F cos theta times delta x. Alright. So we have,
I say why we because
it's the same thing.
let's say they won't give you a mark for that.
It's the same thing. It means you identify that multiplicative is committed. They won't give you a mark, but you're not wrong for writing it either.
But you must write it after you wrote the correct formula.
After I wrote the correct formula.
Not for the course.
And this equals 500 times 20 times 1, which is 10,000 joules, 10 kilojoules. 10,000 joules. Maybe that's not necessary when you're doing currencies. So just
commas
put
not
joules.
necessary.
But it kind of separates the three things, so you can see whether in the thousands, the millions, the.
So leave it like that. Let there be space between the first part and the second part. If it's 100, it must be 100, and then the 3 zeros to indicate it's 1,000.
Alright, we'll leave the space, So 10 kilojoules, 10,000 joules. Wow, okay. It's quite a lot of work. Can we compare 10,000 joules with something that we know? Or you're looking at the food wrapper?
Okay, this is the daily amount on average about, which is
Wait.
8,500 kilojoules.
Is that the amount of energy in the chocolate bar itself? Or they're recommended for a full adult? Okay, cool. So it's how many joules?
8,400 kilojoules.
8,400 kilojoules.
It says kg.
Kg.
Kg is.
Let me see that.
Yeah, at the bottom.
Guideline daily amounts of. Oh, okay. An adult needs 8,400 That's 8,400,000 joules every day.
For them to just function.
For a human to just function, yeah.
Yeah.
And the car to just move 20 meters at a force of 500.
Don't you think that we can start a car with just giving the
I don't think it's impossible for humans to discover or figure that out. But what would it take?
on the light bulb on my phone. So
But what would it take for humans to do that at will? That's the question we have to ask. Anyway, okay. So 100 grams of Tex chocolate bar will give you 208 kilojoules, or per serving, costs 2,088. So a serving of Tex, this is a 18-gram bar, gives you 376 kilojoules. So the amount of work done on the car to move it just 20 meters goes into this chocolate bar like it is 37 times. But just to move the car 20 meters and speed it up.
Like, if we work together, so I think, Nay, we could stop load shedding.
I mean, next question.
But sir, think about it. Like, sir, I give you time to think about it. You don't think about it at home or something.
I mean, I'm not gonna say that's impossible, but it would be curious to see how that unfolds. If that happens in my lifetime, I'd be like, yo, isn't that something? So now, we're told that the same car, which now has to slow down, is slowed down and a force of negative 300 Newton is applied in the opposite direction. And this is done whilst it travels a distance of 25 meters. So the car is still traveling in 25 meters, so in the same direction to a distance of 25 meters. But now the force is applied at an angle of 180 degrees, so in the opposite direction. So force applied in opposite direction. By the way, over here I put the cos after the F because it is a component of the force, not of the displacement. Because we're told that the force is applied in that direction, and in the second part, force is now in a different direction. And then same direction as before is 25 degrees. So now the work done by the brakes. So work done by brakes equals the force times cos of 180 degrees times the change in displacement, where this is just the force component and this is the displacement component. Then this becomes minus 300 times cos of 180 degrees multiplied by change in displacement, which is 25, and this gives us how much?
Negative 7,500
joules. Okay. So if just based on the outputs of the work, the amount of work that is done to push the car, to increase the car's speed over 20 meters is 10,000 joules, and it's in that direction. Now the brakes are applied. First, we know that the force is less than in terms of size, and it's in the opposite direction, so it's now slowing the car down. But just in terms of the work done for going forward is more than the work done for going. Which direction is the car going to end up moving just based on the work?
It's still gonna move forward.
It's still gonna move forward, but will it still move at the same speed?
No, because it's slowed down.
Yeah, because it's slowed down. So again, the answer must be negative because the applied force and the displacement are in different directions. This means that there is energy being lost by the car, and this may also be energy lost as heat to the environment. However, conservation of energy still holds, and energy has just been transferred to a system that contains the car.
Yes.
Yeah, so
There is no Bluetooth to the current.
the brake pads as well,
Yeah. And then the traction of the tires.
traction of the tires as well. Yeah. But mostly the calipers,
I don't know what that is, but
the brake pads.
okay.
Calipers means something that clamps.
Oh, okay.
There's a measuring unit called calipers, so it's like a ruler, and then you can measure internal and external. So like you can put it in between this trench here, and measure the distance to 0.00 to 3 decimals accuracy. Just measure like a ruler, but more accurate. You can do that for inside here, and you can do that for outside here, even for objects. So you can get the accurate measurement of the width of your phone, the thickness of your phone, etc. And then the what can you get it?
Mhm.
And like
How do you say?
I would like to think you could, but we used to use it in a specialist laboratory for civil engineering materials. So, but you could probably get it at. I'd like to think a store like Coastal. I'd like to think so, but I doubt. But maybe a hardware store. Maybe a hardware store.
Just use them. So maybe please refuse them.
Reduce it.
Thank you.
Reduce it. Okay. All right. So now, a box is being pulled at an angle. So I want you to think about it this way, ne? The force applied on the box. So this is worked example number 3 on page 225. Right? So the box is pulled at an angle that is 60 degrees to the horizontal. Right? The force is 20 Newton and the theta is 60 degrees. Not Celsius, just 60 degrees.
But to say. Why would it be Celsius in the first place?
Why would it be what?
Celsius in the first place.
If it's temperature. I'm just putting it out there. So.
Let's see if I get if you said it's not Fahrenheit. Okay.
Yeah, it's not Fahrenheit just because the force is written with a F.
Yes.
So yeah.
Getting ways.
But anyway, we're told, I thank you. That we're told that the distance that it moves.
That's
I know it's not, but I'm receiving it nonetheless. So thank you.
And I also can't say you're getting better because you're gonna still say thank you.
I receive. So yeah, so now we're told that the box is pulled at a force of 20 Newton, that is at 60 degrees to the horizontal, and it moves a distance of 5 meters, right? We need to find now the work done on the box, and the work is simply the force times the inclination of the force times the displacement. And we know that the force is 20 Newton, the inclination is 60 degrees, so we take cos of the inclination, and then we multiply by the distance that it travels, or the displacement rather, and this becomes 100 times cos 60. Let's just see special triangles, 1, 2, 3, 60, 30, so that would be a half, so it would be 50 joules. And the answer is positive, meaning it's in the direction it was moving in before. let me just put that there in the same direction as motion. So in the same direction it was moving, the same amount of work is done on it. Let's just do a couple more minutes. Let's say 15 more minutes, and then we can go for like a short break, like maybe 50, it's gonna be half an hour, and then we can come back for class at the next class is 2 now. I switched off my do not disturb, so
Well, for me, it notified me that it's in 30 minutes.
it's in 30 minutes. Okay, so let's take 15 more minutes during this, and then 15-minute break, and then we're gonna start in 15 minutes. Yeah. Because I just want us to discuss network, because we did discuss it on Saturday. Network. Yeah. So network.
WorkNet.
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 Yes, that's why I'm smiling, because I remember you had something funny, comical that you coined for it. So we've only looked at a single force acting on an object. So then if multiple forces do work on an object, then depending on the direction, I suppose, we'll have to find a network, a work net, the work net. So,
So network is Vodacom and Telco. Please.
So we call the work done after taking into account all the forces. So the work done, so rather network is work.
Sir, please write WorkNet.
WorkNet, oh, I must write WorkNet.
Yes.
Okay, not network.
Yeah.
I'll remove,
We have to
okay.
erase so you didn't have to erase everything. No.
WorkNet. I just like the action of erasing the thing. WorkNet is work done after taking into account all the other forces, taking into account
The other forces.
work done by all other forces on an object, work done by all other forces on an object, all other forces on an object. Alright, so there's two approaches. We can calculate work done by each force,
Individually.
by individual forces. And then some of them take into account considering signs and directions, and then 2, we can calculate the resultant force from all the forces acting, and then calculate the work done using the resultant force. So find resultant force, and then afterwards the work done by the resultant force. The work done by resultant force. Alright. So if we're gonna
So personally, I'm going to use approach 1.
approach 1, why? What?
I feel like it's going to be much easier for me.
I feel like it's gonna be easier for you.
Yeah.
I guess anyone would go for the approach that works for them best. I would also encourage just knowing how both approaches work, so that if you're familiar with both of them, and then you for some reason it just builds I feel it builds a sense of confidence knowing that if for some reason I experience a jam, I can always think of the alternative method. But
So stop trying to be as funny as you.
I'm not trying to be as funny as you, I'm just being as funny as me, whatever that funny as me
So
is.
you're not funny.
I'm not funny.
No.
I'm not funny.
No.
Oh, that warms my heart. Approach 1, calculating net work on a car. Okay. So worked example number 4, right? Yeah, it is number 4. So approach 1, and this is on page 228. Using approach 1. That same car is now accelerating forward, but friction is working against the motion of the car. So a force of 300 Newton is applied forward on the car. So we'll say it's positive, just to keep the signs in check. And then this is applied whilst it's moving a distance of 20 meters. The frictional force of 100 Newton, so acting in the opposite direction of the motion, also acts on the car. So now let me just draw a car to remind us what our scenario looks like. We've got libidi, base of car, bonnet, body, boot, and windows. Karke van, karke fancy.
So.
Karke fancy.
Oh, songs. You just remember that song.
Yes, because karke pants.
It doesn't look like a pencil. It looks like a concert.
Looks like a cosa. Karke cosa.
Say how.
So now we know that the force there is 300 Newton in that direction, but I'll use a different color for friction.
So can I ask? When we're using this, do you have to, is it, why am I going with this question? What I'm trying to ask is that, do you have to put all the 4 components? I guess it's going to be like normal force, an FG, you're going to have the friction, and the applied force. Do you have to calculate the net done by all those
forces?
Or
that's a good question. I think it has to do with what's necessary in the scenario. So in this scenario, our angle is 0 degrees. So we can put that in the analysis, and we can include normal force, but we're gonna find that the angle for normal force is 90 degrees.
Which is going to be
0, and then
for FG as well, it's going to be
0. And we can probably only just have an idea of the weight of the car, but we're not given its mass, so it doesn't really help us to include that in the calculation. Yeah, so, but we can do, because normal force would be based on the weight anyway. But the angle would also be 270 degrees, so cos of 270 would be 0. So it doesn't serve us to include it in the calculation.
Okay.
So good question. I'm just going to make here a note. Normal force and weight act on car. However, but, a big but, okay, maybe not big but like a big however. Because but changes the meaning of the sentence. It changes the sentence. However. The sentence.
So you said sentence.
Sentence. Ish, absurd. I didn't realize I was saying sentence.
But you know that happens to me a lot. My words slip.
I think it's called spoonerism. Let's see if ChatGPT knows a couple of spoonerisms.
Yeah, it is spoonerism. Where like you switch the letters.
humorous examples of spoonerism.
The last time I heard of spoonerism was in my English paper one last year, November.
When you wrote about those in the exam. Wow, okay. So I was saying, so theta for normal force is 90 degrees and theta for weight is 270 degrees, and at these angles cos theta equals 0, therefore no need to include N and W. So I just thought I'd put that out there. Alright, we're just going to finish up just one more minute. So now we can go back to our analysis, and the work done would be, we said approach 1, which would be force 1.
We approach one, I can't be calculating them individually.
No, approach 1 is find the work done by each force acting individually. Oh, yes, that's what we said.
Yeah.
So F
So you
cos
calculate friction
theta.
first, you calculate applied force.
So this would be the first one
For friction.
for the first force. So call it F, and then the work done by friction would be Fk cos theta times delta x equals, so that equals, so this here would be 300 times cos 0 times 20 meters, which is 6,000 joules. 6,000 joules. Okay. And the second one would be negative 100 times cos
180. Cos 180. So why are you saying negative 100?
Yeah, that's why I was silent for a minute there. Times cos 180 times 20, and that gives us
Negative 2,000.
negative 2,000 joules. Right, then the work net would equal 6,000 minus 2,000,
which is equal to 4,000.
4,000 joules. And then approach 2 would be simply calculating the resultant force acting on the car. So the resultant force would be the sum of all the forces. So it would be F plus friction, which would be 300 Newton plus negative 100 Newton, which is 200 Newton. Then network will be 200 times cos of 0 degrees, because we know that the dominant force is in the direction of 0 degrees, and then the displacement is 20 meters, and that should be 4,000 joules. This is approach 2. And then we can go for a short break and then come back for math.